Hello, everyone. My name is Ionel Ghiță. I'm the Automotive Ethernet Technology Specialist and Industrial Time-Sensitive Networking at Keysight Technologies. Today, I will cover a personal passion of mine, autonomous vehicles. In the session today, we will cover the definition of a self-driving car, the circulatory system, the sensorial system, and the nervous system. At the end, we will have some conclusions, some funny fails that I found over the internet by browsing and researching, and a challenge in terms of legal aspects of certifying a self-driving car. All the copyright of the material presented in this presentation belongs to their rightful owner. This session is posted for educational and informational purposes only. This is my personal research that I want to share with the outside world. In this session, I will use several acronyms, and I want to be sure that everyone knows what it means. ADAS, for example, stands for Advanced Driver Assistance System. ECU stands for Engine Control Unit. Tier 1, Tier 2 are basically the system manufacturer and the component manufacturer depicted here. SCU stands for Speed Control Unit. These are the terms that typically are used in the automotive ecosystem. What does it mean, a self-driving car? What does it mean to be an autonomous vehicle? Now, this is the ecosystem that builds these autonomous vehicles. These are all the companies that are deploying technologies to build the next generation of vehicles. On the bottom, you can see the development tools. This is where Keysight also helps the environment to test all these technologies. From left to right, you can see the developing of processing, sensors, connectivity, all the machine learning algorithms that are integrated into self-driving vehicles, and also the security part of all this software being deployed. On the top side, you have the vendors, the OEMs, and immediately after that, the new tier 0, I would call them, the Waymo, the Uber, the Lyft. These are the ones that are taking all this autonomous technology and put it on large number of vehicles for all of us to use. The middle one is the tier 1. These are the technology that produce the components that are integrated into these self-driving vehicles. From the left to the right, you can see all the logos for their specific applications. The top ecosystem is called the OEM. And immediately underneath it, it's the new, let's call it tier 0. It's the new companies that play an important part into the autonomous vehicle ecosystem. These are the Uber, Lyft, Navia, and all the companies that have large ecosystem of vehicles that they want to have them autonomous. What means an autonomous vehicle? SAE, the Association of Engineering for Automotive, designed a framework, a legal framework that defines the features that are integrated and produce the autonomous capabilities of the vehicle. It's not the vehicle that is certified to a specific level, it's the features of autonomy in that vehicle that makes that specific classification. These are some examples. What does it mean, level 1 autonomy? It's the feature that is developed in most of the cars right now when deployed, like cruise control. That's level 1. More complex features go to higher levels. The most advanced autonomous vehicles deployed in the road have features which are certified in the level 4. So they are capable of driving themselves in closed campus operation or specific geofencing. There are other legal compliances that need to be passed. For example, the ISO, which is the functional safety, and there is another UL standard currently for the certification and the safety of autonomous vehicles. Where we are standing today. So today we are in the, I would say, in the level 3. We have some conditional automation. We do have some features that enables vehicles to allow us to be a little bit not in control. The legislation, however, says that at all times we need to keep our hands on the wheel. In the next period of time, my expectations within, I would say, 3 to 4 years from now, we will have features that we only need to be aware of the environment. We do not need to keep our hands on the wheel. in maybe 20 to 30 years from now, we will have vehicles which will no longer have a steering wheel or brake systems. They will be completely autonomous, and we will be only passengers. There will be no driver. So the concept of driver license will become obsolete in maybe a decade from now or 2 decades from now. That was the legal part. But now, from a user perspective, what does it mean? So this is a model developed by Dr. Philip Koopman, the driver-centric way of looking into the automation. So we right now are in the assistive part. The human is still required to drive the vehicle, requires a driving license, and in case of an accident, he's legally responsive of the incident. Some vehicles, they are supervised. They have features which enable a high level of autonomy. Still, the user is the one legally responsible for everything. In case of a specific failure, the user must take control of the brake and the steering wheel. What I wish for, and this is where the industry is moving, is towards automated vehicles, where we just plan the route and the vehicle will take us there. In a while from now, the vehicles will be completely autonomous, so no human driver is required, and they will be able to take all the strategic decision. If you don't mind, could you please put yourself on mute? There is a lot of noise coming from your side. So talking about the analogy with the anatomy. So my thoughts were to take apart the vehicle and take it system by system. So now we are going to talk about the backbone of the vehicle, the circulatory system. So a little bit of trivia before. Do you know what is the heaviest component in the car? That is the engine. And also that is the most expensive component of the vehicle. What is the second heaviest component? Well, are the cables and the harness. It's all the things that takes the energy from one point to the other. How much these cables are actually in terms of weight? That's around 50 kilos. That's 110 pounds. And some complex vehicles are even heavier. And how did the industry respond to that? Well, a new standard came, which is called automotive Ethernet. It takes the technology from the telco and the internet that we know today and adapt it for autonomous vehicles. This is a very simple depiction of how it looks. Keep in mind that this image does not contain the components. It's just the wire harness and the connectors to attach to different systems that are part of this vehicle. The most advanced vehicles have a much more complex harness. Now, how is this architecture constructed? Basically, there are two types of domains. One is the domain-based architecture, which every specific functions of the vehicle share the same bus with others and also the same energy distribution system. So this is what circulates data and energy. And all the components are clustered based on their functions. So body domain have all the sensors that are specific to the body, and there is a controller unit which communicate with all the others. So in case of need, they only communicate on this data bus the information that is needed by the other functions of the vehicle. This is a very high-level view of how a domain-based architecture works. So there is a central gateway that takes care of the communication with the outside world, but it's also kind of gatekeeper for the other functions of the vehicle. As I mentioned, they share the common bus system, and all the functions are taking the information from this bus system. Unfortunately, this is sometimes a single point of failure. So this design can have faults, and in case of a software issue or a hardware issue, the entire vehicle becomes unusable. And it's also not safe if something goes wrong, if it's hacked or it didn't survive a physical incident. A new design, which is getting much more traction from the industry, is the zone-based architecture. In simple words, it is a distributed system where each zone of the vehicle have their own switching capabilities, and they are processing locally the data that comes from the sensors. They share a common backbone, which is depicted here in red, which is a high speed, and all the high processing functions are done as close as possible to this core. what kind of protocols are used in a vehicle? What type of interfaces? This is a very short example of some of the protocols that are used in the vehicle. CAN has been there for ages. It was invented as a simple protocol between for communication between sensors, engine controls, powertrain, and chassis. There was the need, because this has only 1 megabit, there was the need to improve this protocol. So a new version, which is deployed in the vehicles on the road today, can lead up to 5 megabit. Most was invented mostly for multimedia, and it was one of the highest speed protocols used in a vehicle. And then there was the need of a very high redundancy and a very, highly certified in terms of safety. So FlexRay had the promise of 10 megabits, and it's used for braking system and everything that has to do with the safety of the vehicle. Automotive Ethernet came into play mostly because of infotainment and multimedia streaming and all the cameras and all the sensors that are producing a lot of bandwidth. So there was no other infrastructure rather than to take a new technology and deploy it in the vehicle. And Ethernet was there. The internet is made out of this Ethernet protocol itself. And with the connection of 4G, 5G, and V2X, it came natural to use the same protocol with the outside world within the vehicle. Now, we've talked about the circulatory system, but what is the heart of the vehicle? Right now, the heart of the vehicle is the generation of the energy and the power distribution. So the power distribution unit is similar to a heart. It takes the energy from the source and distributes it toward the system. And there are many things of this energy. The climate control, it's one of the highest energy saving system. Power steering, braking system, all these kind of functions are consuming energy. This is a very short depiction of, from batteries point of view, what are the energy consumption of each system. Some technology decided to, a technology that was available in the regular internet, like power over Ethernet, was also implemented in vehicles. It's called power over data lines, and it's capable of delivering up to 50 watts to the systems connected to this model. Now I have a good news. The power box that we all know, the thermal fuses, are going to be obsolete. There are advancements in the technology, and heavy wires will be removed because these new technologies are capable of delivering the right amount of power over thinner cable. So that means less money for the development of the harness and less weight to the vehicle itself. And this is a simple schematic how the future of these power distribution systems will look like. Have you ever wondered how a car looks under all the metal and all the glass? So this is the depiction. This is the circulatory system of a vehicle. This is all the wires that goes to all the nodes in the vehicle. As you can see, some of them are bunched together. Some of them are just taking the information from the sensors and lead that information to the powering, or to the processing units. This is another view from a different angle. And you can see here that there are two batteries. One is for the engine to start, and the other is for the accessories. The one in the back, it's actually keeping the entire system alive. In case of power loss, there is always a safety system in the vehicle. This is inefficient in a way, because the weight of the vehicle is artificially increased just to be able to power all these systems. So the advancements in these new technologies simplifies a little bit this wire harness and also takes the weight of the vehicle. It helps a lot, especially in the CO2 emission. Less weight means more fuel efficiency. Now, we have a circulatory system, but what about the sensors? How the vehicle perceives the environment? How does it know what it needs to do? A modern vehicle, an autonomous vehicle, will have a lot of sensors: cameras, radar, lidars, sonars, GPS, V2X, all kind of accelerometers, gyroscopes, and a car doesn't know if it's sliding on ice or it's muddy. Where does it go? So it needs all kind of sensors. We as a human, we know that we are when we are in control of the vehicle, we know that the vehicle is not behaving normally. The autonomous vehicle needs to have all these sensory capabilities. In this session, I will talk only the first three of these capabilities that are deployed in autonomous vehicles. The first one is the camera system. Cameras have evolved a lot, and new technologies are cameras with no moving parts. Everything is solid state and it's highly reliable. New cameras, specifically for autonomous vehicles, integrate machine learning algorithms. They have the capability of processing the image in real time and giving on the wire only the information that is required for processing. Now, on the right side bottom, you can see a stereo camera. This has the same perception as we humans do. It has the capability of depth perception. And all of the processing of the image is done directly in the camera. So a lot of offload, it's performed locally, and no processing is required from the central CPUs. Some interesting data about camera system. So some cameras are for the visible light, the light that we see, but there are cameras deployed in autonomous vehicles which are in the infrared spectrum. They can see through rain, they can see in night, and they can see through fog. This is a way of our human perception capabilities. Some vehicles, especially professional vehicles, are also using thermal imaging sensors, especially to avoid danger in the environment that they operate. A vehicle will have typically between 5 to 6 cameras. The more advanced vehicles will have up to 12 units. And this is a small description in the amount of bandwidth each camera for the specific resolution is used. So as you can see, there was the need to implement a new standard to deliver this high bandwidth data from the camera towards the processing unit. When talking about cameras, codecs cannot be used. So most of the data is uncompressed because of the latency. Codecs introduce latency, and autonomous vehicles cannot afford this latency from the acquisition until the moment it's processed. So how does it see? How the camera sees the environment? It doesn't see the way we do. It is processed through machine learning, all kinds of complex algorithms, and takes only the information that is relevant for the driving action. What is the object shape? What is the direction? What is the speed of direction? And what could cause an environment hazard? And I have here an example about shape recognition. This is directly from the processing from a camera displayed so that humans can understand how the computer sees the environment and maps the object recognition towards the shape. So in a urban environment, there are a lot of risks, and the camera is capable, the cameras and the autonomous features are capable of processing all these hazards in real time. Besides cameras, autonomous vehicles deploys senses that we humans do not have. One is short-range radar. It uses a specific spectrum of radio frequencies and sends short bursts of radio information and then listens back that specific mapping of the environment. Typically, these short-range radars are up to 30 meters. They are mostly used for collision warnings, pre-crash sensing, stop and follow the vehicle in front, especially in urban environment. They are used also for pedestrian detection. So if somebody tries to cross the street, the vehicle will be able to stop and not harm that specific pedestrian. And also parking aid. So whenever you're trying to park, the vehicle will know exactly if the spot decided it's the right one or not. There are also long-range radars. This is especially for the operation up to 1,000 feet. This is the road awareness of the vehicle, and they operate in a higher frequency, and they have a discrete form of quality. Depending on the environment, they can change the operating bandwidth, and they can do a full mapping of the vehicle or the hazard in front of it. Typically, these long-range radars are used for motorist detection, object detection on roads, for example, stones, broken pieces of trees, and all these kind of things that could harm the vehicle or the occupants. It's also used for adaptive cruise control. So the vehicle is capable of keeping a safe distance on the highway from the vehicle in front of it, and it knows exactly when it's too close or when it's too far, or when somebody is cutting off in front of it. Another very interesting feature, it's for the long-range radar, it's when a passenger tries to get off the car. So this actually notifies if it's a risk, like somebody on a bike or another car coming. The car will be able to say, do not get off the car right now, there is a hazard. Please stay inside, it's safer for you. Also, these long-range radars are used by the autonomous vehicles to find the appropriate parking place. So do I fit in that free spot? And it's through the 7 gigahertz bandwidth, it's capable of mapping correctly the environment and take the all the data that it needs to figure it out if the environment is also safe for the vehicle. Now, besides cameras, there are other sensors that uses light. And there are two terms for the LiDAR systems. One is light, one is laser. Typically, they emit a source of energy, which is visible or invisible, and then takes that energy back from the environment and maps the environment. So there are two types, distance to object and also Doppler. Doppler is capable of actually measuring the speed of an object which is in that specific angle of view. Light emission depends on the type of target. There are infrared that could see way beyond the humans can see. They are sometimes in the visible light, but also they are a high resolution in the ultraviolet spectrum. I have here a little bit of mathematics, how actually these LiDARs work. It's highly questionable, my mathematics in this example. It's much more complex than this. So how does the LiDAR see it? This is a very simple example of a short range LiDAR in an urban environment. As you can see, it maps the environment and it's capable of detecting all the moving objects within this specific space. And farther away, you can see that the colors get more closer to red. So it's capable of detecting the range, the movement of the object, the height of the object. So this LiDAR system is detecting also if the vehicle is safe to pass, for example, bridges or underground parking places and all these kind of things. How does a long-range LiDAR works? So typically these are on top of the vehicle and they scan environments to really large distances. So they are environment aware, vehicles, environment, trees, buildings, and all kinds of things. And on the highway, they can actually detect dangers up to one or 2 kilometers in front. We are humans. As humans, we could not see as far as this LiDAR system goes. These are typically moving parts, so they spin around 300 to 500 spins per minute, so they can have a very high accurate and real-time view of the environment. When I've made this presentation, there was a public announcement, so I have a bonus slide for you. I was not aware of this technology existed, but right now there was fresh from the R&D labs, a new technology is going to be deployed for autonomous vehicles, and that is X-ray. So there is a new technology that is capable of passing through objects and see hidden risks behind those. So here, for example, it's a bicycle behind the bus. This is outside of the capabilities that were in the cameras or in the LiDAR systems. Here it's another example when a vehicle is moving from right to left through a city, and it's considered to be a hazard because it's passing a red light. Another example, it's a schoolboy that is trying to jump in front of the vehicle. Without these X-ray technologies, this hazard could be very difficult to avoid normally. So this new technology, I encourage you to search this company, and they have a very nice demo video about the new implementation of this X-ray system. Some example, how all these sensors are combined, how they are all put together. These are several prototypes of autonomous vehicles, and these are several deployments of all of them put together. This is one system from Apple that has a lot of sensors, as you can see. So in all the directions, in all the angles, in all the views, cameras, LiDAR system, short range, and also communication systems to be aware, to be connected to the cloud and to the debugging systems. This is another example from a Lexus car, a different deployment. You can see also 2 antennas of GPS. There are a lot of cameras, LiDARs, and radars connected to the rooftop of the vehicle. This is another POC done by Qualcomm, where in this vehicle there were 16 cameras mounted all around, radar and all kind of sensors to collect as much information as possible from the environment. And this is one more advanced prototype from Uber that also has, as you can see, a lot of sensors, a lot of cameras deployed on the rooftop. Of course, these are prototypes. Probably the end vehicles will not look like this. I've talked about the energy, the protocols, I've talked about the sensors, but what is processing? What is the brain that is processing all this information? And actually, how does this brain work in a vehicle, in an autonomous vehicle? This is a depiction of the processing components and all the CPUs and ECUs deployed through a vehicle. There are a lot of technologies which does more than taking the passenger from A to B. It's processing all the car signaling, and it's taking the right decisions. Now, I've talked about zonal architecture. There are several advantages. In case of a crash, having this kind of redundant network gives advantages of the vehicle to be still capable of driving itself. In case of failures, some functions can be transferred from a computer to another computer. You know, in a car, water can get in. What happens if one ECU goes off? Well, the other ECU could do that job. And all this redundancy is required for autonomous vehicles because human will no longer be required to be there. Also, there are going to be intelligent gateways deployed. So that means that the cloud will be connected to the car. So the car is just another component of the data center itself. These are few examples of the brains that are deployed in the vehicle. These are two vendors that made these ECUs, and these machine learning algorithms are deployed on these machines. This is how actually, these are the interfaces from one of these machines. So some of them we know them already, like HDMI, USB, and all these kind of things, but there are protocols which are specifically for automotive application. And what's inside the brain? Oh, well, these are two major components that I found in my research. One is the Tesla, the other one is the new project from NVIDIA. This is computers that are designed to run a lot of machine learning algorithms. And they typically have redundancy. They have a lot of interfaces to process, to gather the information, to process it, and then take the decision for the driving itself. NVIDIA also announced a smaller version that is mostly for the deployment in redundant systems. So you take a lot of these computers, deploy them in the vehicle. In case one fails, it's no problem. Another one will take that processing function from the failed system. Now, that was the hardware. What about the software? Software is an important part of the processing. This is an architecture that is defined by AUTOSAR. So these are all the software components that are required for an autonomous vehicle. These are all the protocols and all the small bits and bytes that are required in the software to interface with other systems. Besides the processing unit, all these stacks needs to be properly tested, needs to be properly deployed, and there is thousands and tens of thousands of lines of code that interact one with the other. On top of this suite, this specific stack, it's the application. It's what the autonomous vehicle company is building itself. What are the decisions, what is the software, what are the features enabled, and so on. So the complexity of an autonomous vehicle could get way beyond hundreds of millions of lines of code. Now, a new technology that is deployed in autonomous vehicles is the virtualization. This is an example from Cisco. They have made a virtualization software, which is called PyCOS, and is doing exactly what any other virtualization system is doing. It's taking the hardware and it's giving functions to the application that are run. This is highly efficient in terms of energy and also in terms of resource utilization. So in specific cases, when the engine is stopped, you can deploy the application in a single computer to save power, to save processing functions. And once you start up the engine, the specific ECUs will start up and take all those virtual machines and process them locally. It's also, from functional safety point of view, it's highly used. If something goes wrong, there will be another computer that is capable of taking exactly the same functions and perform all the needed safety checks. So how all these work together, how the nervous system processing. So it senses the environment, then it's using a lot of machine learning to perceive the object, the speeds, and all the kind of environment hazards. Then it takes a decision. I want to do that, or I want to brake, I want to take control of the steering wheel. And then it's actually the control of the steering wheel. So there are all kinds of components which make these movements, like pushing the brake, changing the lanes, having the action itself. So how does it work? It's a lot of machine learning and a lot of processing. And the neural networks that makes this system, they are typically put together in several layers. Now, on the right, you can see on the right side, there is a picture with how the human sees the environment and how actually the vehicle sees the environment. So all the red boxes are considered hazard on the road, and all the part which is green is considered safe objects. So this is the difference between what we see and what a vehicle sees and how it takes the decision. There are a lot of history and histograms of gradients, a lot of machine learning that is learned from other vehicles and deployed in this vehicle through cloud updates and all these kind of technologies to improve the learning functions. Now, as an example, this is a small demo from Tesla, how the neural network of Tesla works and how they decide to take the actions and how they perceive the environments when they are driving. And for some reason, I need to, okay. So this is how Tesla sees and acts on the environment. Whatever it's a red means it's a risk. Whatever it's a green, it's a good to go. And static objects are typically in blue. So this is an urban drive. This is through the streets, and it finds the street signs, it finds the objects, it finds all the risk, and then it also recognizes the patterns on the environment, all the white lines that we know as a humans we need to avoid or we need to pass through them. Conclusions. So first of all, autonomous vehicles help us be more friendly with the environment. The electric vehicles will be the dominant market for autonomous vehicles. And machine learning and all the algorithms and a lot of frequent updates, just like our phones, will improve these functions of autonomous vehicles. Automotive Ethernet will be soon the backbone of the car. So we need a lot of bandwidth. We need a lot of data passing from one sensor to the processing engine, from one processing engine to the other processing engine. So my expectations are that automotive Ethernet will be the spine of the vehicle soon. However, we need a lot of infrastructure upgrades for autonomous driving. First of all, charging stations. We do not want to have diesel and gas. We want a highly available charging system. We need to have the capabilities of having vehicle power sharing. We need to, if in case of low battery, what you do in the middle of the road. So cars should be able to assist other cars and share their energy. We need smart roads. We need vehicle to network. We need the car to be aware of the environment. We need to know if an accident is in front. We need to be sure that we can avoid it, and also we can reroute in real time to avoid these kind of road blocks. We need smart cities. The vehicles should be aware of the environment, should be aware of the city it's driving into. So this infrastructure needs to be deployed. It's not that there are several prototypes deployed in the world, but the infrastructure needs to be deployed to assist autonomous driving. The car needs to be an extension to the user. Like today, Bluetooth. You take the Bluetooth from the phone, you connect it to a speaker, and the flow is similar to most of the Bluetooth speakers. The cars are not like that, and they need to become like that. To be, regardless of the brand or the system, the car should be the same flow. The workflow from the user point of view. I'm getting into the car, I'm getting to the destination, I'm getting off the car. Regardless of the vehicle or the features it has, they should all have the kind of same feeling. My expectation is also a lot of startups will rise in the automotive, artificial intelligence, machine learning, and the cybersecurity space. There are a lot of computers in the car. So also that is a good place for the hackers to get in. So new hacker groups will appear and will try to take control of these new computers on wheels. Now, in my research, I found some funny fakes. So I want to share with you some of the things that I found. It looks like Google cars are quite timid. Whenever they try, people are conservative in terms of driving style. Some of us are a little bit more aggressive. Google cars are timid. They are very, very safe in this point of view. If you wave in front of the car and you do not cross the street, the Google car will wait for you. If you are doing that, you are actually trolling the car itself. If you jump on the street and then back and wave the hands and jump again on the road, the car will wait there, will not make any move because it says, okay, you need to pass the street. So it's timid. Waymo, when they deployed the vehicles in US, they got stuck on dead end street. They were aware of that map, but they got stuck. And people in that residence started to complain about Waymo cars getting stuck there. And, they had to be overridden. Human had to take control of the steering wheel and take the car out of that specific street. Autonomous vehicles are highly deployed, or autonomous vehicle features are highly deployed on professional vehicles like trucks. And that means a lot of jobs will be lost for these autonomous vehicles. And one of joke is that my truck left me by the stairs. This is where most of the use cases are actually, helping a lot for the professional vehicles to be as much as possible autonomous. In the Tesla algorithms, in the Tesla machine learning algorithms, there is a process called chiropractor adjust skeleton. And I encourage you to Google it and see exactly what this specific function is doing. Another one, which is also quite funny, a car got stuck and the software got stuck when a duck was on the road. As you know, ducks are quite, not smart animals. So the duck was moving a little bit, the car was moving a little bit, the duck was moving a little bit more, the car was following the duck. So it got stuck in this loop for quite a while. And as the duck didn't move away, the car did not proceed. We as human, you try to force a little bit your luck. The autonomous vehicles are not there yet. And another funny example, it's a self-driving race car waiting at the, waiting at the line. As soon as the lights get green, makes a sharp right and crashes into a wall. That was funny. And this is, why we need to invest more time evolving algorithms, testing all these algorithms, and, do as much as possible miles on the road with autonomous vehicles. Now, I said that I have a small challenge. I've spent a lot of time reading the legislation, going through the standards. And my question to you, this vehicle, can be certified as an autonomous vehicle? Technically, yes. It does have an organic computing capability. It has a lot of senses. It has environment awareness, and it has voice control. So it knows what to do and it takes those decisions. However, it cannot be certified, and at least I find 3 points that this vehicle cannot be certified. We cannot do pre-crash and crash test with this. There are animal rights which does not allow us to do that. It does not comply with manufacturing investigation in case of failure. So we cannot do the event debugging if something goes wrong. And also another requirement, it says that event recording, like a black box, should be available on the vehicle to be retrieved in case of failure, root cause analysis. However, on the internet, on the YouTube, there are good examples that level 4, where the user is optional, has been achieved. So this is why I have this kind of challenge with myself. If this, horse-driven carriage can be actually certified as a level 4 autonomous vehicle. I have several references if you'd like to watch more about Professor Philip. I encourage you. There is a amazing blog on these technologies. There are all kind of demos about autonomous driving, and also there's interesting blogs from Tesla and Waymo on their technology for autonomous vehicles. I will open the mic now for questions on the line.
Hi,
Hey,
can
Ionel.
you? Oh, sorry.
Sorry. Hey, Ionel, I believe you have some questions on the chat.
Oh, okay.
Yeah, notes, questions.
Okay. So I don't, unfortunately, I do not see the chat window. For some reason, Teams is making me a little bit hard. Is there any, I could not, if somebody has the capability of reading the chat, I cannot see the chat in Teams, unfortunately. If there are
I'll
any
email
questions on
them.
the line,
I'll email them to you. Maybe until then, if you can get Stefan's question. I
please.
believe he was the one.
I was wondering what opportunities for self-driving development are for engineers here in Romania.
There are several companies and there are several new upcoming technologies, startups that are developing machine learning for all kind of functions for the autonomous vehicle. There are also tier 1 vendors that have R&D offices in Romania. Now, it all depends on your interest, but the opportunities, there are a lot of opportunities, and there are a lot of opportunities that will appear in the near future.
Well, as far as I'm concerned, I was wondering about more like software developments or not actually hardware, or perhaps hardware too.
So at Keysight, we built the software that actually tests a lot of the infrastructure in the vehicle. So all the communication protocols, the communication with the car, with the outside world, this is what we do. I can only comment on what Keysight has right now in terms of the research and the technology that we build to assist these vendors. As you've seen, the ecosystem has hundreds of companies that need to test before deploying these technologies in the vehicle on the road.
Thank you.
Welcome. If there are any other questions, please. Now, I have a question that pop up on my screen. Do you trust autonomous vehicles? Oh, well, seeing whatever happened in the demos and seeing all the incidents that were reported by different companies, I do not really trust right now an autonomous vehicle. I think we still need to have a lot of miles to train the algorithm, and we need to do a good job in the certification process. So it's one, deploy, test, and then certify that that is safe. Right now, the human is the main cause of accidents. It's true that autonomous vehicles are much safer than the humans. However, there were several incidents where the software got weird and incidents were reported. Most of the other incidents were also because of human failure. So the autonomous vehicle was just a victim, and it had a bad light, let's call it like that, on the autonomous vehicle itself. But I'm still waiting a little bit more until I'll consider to buy an autonomous vehicle.
Hey, this is Ankur. My question is regarding the cyber security, because as the vehicles will become autonomous, there can be high risks for the people, like it can be driven by anyone from anywhere. So is there any progress happening in that front of cyber security?
Yes. There were already incidents of cybersecurity for connected vehicles. Now, autonomous vehicles are more juicy for the hackers. There are efforts. There are companies which are getting together to build an infrastructure, especially for vendors like Uber and all these kind of, they have a lot of cars and they want to be sure that their vehicles are protected. There is also a working group in AutoSAR called focused on the security of the communication protocols and the communication function of the vehicle. So there are also other initiatives that give the framework for this cyber security, all kind of tools, all kind of sandboxing, all kind of techniques to actually fight against this cyber crime. And there are a lot of startups which are raising right now, especially for the cyber security for autonomous vehicles and connected vehicles.